Now we want the velocity with which an asteroid falling from a great distance away would impact the Earth, assuming that the only thing accelerating the asteroid is the gravitational acceleration of the Earth. Now it turns out that we get 99% of the energy if the thing is only maybe 1 moon distance or 2 moon distances away from the Earth. We don't have to get very far away before we have an essentially infinite position at which we get practically all of the energy. Okay, so it achieves practically all the velocity at will. We don't have to let it fall from the next galaxy. Okay, so in any case, if we have a mass m, well, let's stop a minute now. The kinetic energy of that asteroid falling from rest from a great distance away is going to be equal and opposite to the change in its potential energy. What's the change in the potential energy of the asteroid as it falls from a great distance to a distance, say, r? Well, that's going to turn out to be the integral from infinity to r of the force. And we'll set that up in a second. The potential energy relative to infinity is what? It's equal and opposite to the work done by the conservative force. Now, if r is increasing as we go away from Earth, then the force exerted by gravity is in the opposite direction. So if dr is positive, the force exerted by gravity is negative big G big M little m over r squared. And the change in potential energy is equal and opposite to that. Now, if we're integrating from infinity to r, then we're integrating from the greater to the lesser distance. That doesn't change the fact that dr is positive, but we're integrating in the direction opposite to dr, effectively. So our integral is just big G big M little m times the integral from infinity to little r of 1 over r squared dr. And that integral is, well, negative big G big M little m times 1 over r evaluated at r and infinity. And that's going to end up being just negative big G big M little m over r. So that's the potential energy relative to infinity of an object of mass little m at distance r from the Earth. Now that's the potential energy relative to infinity, okay, meaning that it's the loss of potential energy, or the change in potential energy from infinite distance to distance r. So as we fall closer to Earth, we have a negative change in potential energy. This is also the total work done, equal and opposite to the total work done by the gravitational force on the mass little m as it falls from infinity to distance r. So that if the object does fall that distance with nothing to counter the Earth's gravity, it's going to attain a kinetic energy equal and opposite to the change of potential energy. So it's going to attain a kinetic energy equal and opposite to this quantity, which is, of course, this quantity. So we can set 1/2 mv squared equal to this, solve for v, and it's very simple to solve for v. We get the square root of 2 big G big M over r. Now notice that that's the square root of, well, the square root of big G big M over r is the orbital velocity at distance r. That factor square root of 2 tells us that the velocity is going to be square root of 2 times the orbital velocity at that distance. And that's kind of interesting, kind of an interesting connection. This is also the velocity you would have to give something to have enough kinetic energy to overcome that potential energy change. So if we wanted to send something away from the Earth so it would never come back, we would have to give it this velocity when it's sitting at position r. So for example, we could put it at this parking orbit with the moon. R would be the 0.8 of the separation between the Earth and the Moon, and then we could just blast the heck out of it, give it enough velocity that it would never come back. Okay, of course we could do that from any position. If we have it in an orbit at radius little r, then we give it enough extra velocity that, well, if we give it a little extra velocity, we kick it out from a circular orbit to an elliptical orbit, give it a little more, that elliptical orbit gets further from the Earth, and give it not all that much more, and it's going to be a big ellipse that's actually never going to come back. Okay, so we call this escape velocity, and I could write that as V sub ESC, escape velocity, and that's something you might want to stay aware of, this whole picture of the potential kinetic energy changes related to escape velocity.